Hello. Today I would like to present a few notes on probability density in quantum mechanics for single particle states, probability current density, and and I'll attempt to present a formalism that allows us to use that to examine more general properties of the wave function. So for starters, I'll always use the following convention that we define the wave function in terms of its presentation in Bra-Ket notation. So we define what's on the right here in terms of what's on the left. So you already know, if you've done any quantum mechanics at all, it's not obscure to tell you that this quantity, psi star of x times psi of x is the probability density, right? Calling this the probability density rho of x, provided that psi is a normalized ket. That's very standard. What you might not realize, though, maybe you've never thought about it, is that if we write rho of x in terms of the Bra-Ket formalism, if we use Bra-Ket notation to write rho of x, right? Then we got psi star of x and then psi of x, right? Which written in Bra-Ket look like that. And what's interesting here is that you can see very clearly that this has the form of an expectation value. It's the expectation value of an operator that we're going to call rho hat of x. X is a parameter defining exactly what operator we're talking about. And the operator itself is this. This allows us to interpret probability density and probability in general as an expectation value. You could perform an integral over all x of rho of x, rho hat of x, and you would get the identity. And if you perform a partial integral, right? If you perform one from a to b, of rho hat of x dx, which, just to clarify, sticking in our definition, that's this projection operator that you're integrating over. If you do that, you get an interesting thing that I like to call the counting operator. Well, yeah, that tells you how many particles are in the region A to B. It tells you if this is your the real line that this one-dimensional system is defined on, that if A is here and B is here, you can perform this integral to construct an operator that counts the number of particles in between A and B. Yes, this is a one-particle system, so it'll either be 0 or 1, making it a projection operator. But this generalizes very well to second quantization, which I'll show real quickly. As in most cases, this is not a complete hard and fast rule, but just as a bit of advice, you'll find that if you replace x with field annihilator, and x bra with field annihilator and x ket with field creator, when going from first to second quantization, a lot of stuff falls in place automatically. It's not really rigorous, but that holds up in a lot of cases, and this is one of them, right? So rho hat of x in second quantization is so let's follow my recipe. Replace, okay. It's create x, annihilate x. Of course, in order of operation, it's actually annihilate x and then create x. And you can use this to, in second quantization, construct a counting interval operator too that counts the number of particles between A and B, and you do it the same way. It's just the integral of particle density from A to B. If you're in more than one dimension, if you have some region omega, you could count the number of particles in the region omega by integrating, let's say in 3 dimensions, by integrating over omega the particle density, where x, the bar is just a vector hat, to show that this is 3 coordinates. And that's how you could make a little operator that counts the number of particles in a region of space. I guess you're supposed to make diagrams in physics. Here's a diagram. Here's omega, right? We could say that it's like a 2D region of a 2D space or a 3D region of a 3-dimensional space. And this operator n sub omega will count how many particles are in there. As in, n hat is a Hermitian operator, a Hermitian observable, that has discrete eigenvalues, which are the number of particles that could be in here. If it's a 3-particle state, the eigenvalues will be 1, 2, and 3. And if you decompose n omega, you can see that the relative probabilities of each outcome are very, very interesting, right? If you sum it up, like any operator, so let's say from n equals 0 to capital N, where this capital N represents the number of particles in the system. Oh, well, actually, second quantization is supposed to be free of any prejudice as to how many particles are actually in the system, so we'll sum to infinity. And with any operator that has eigenvalues that, in this case we know can be interpreted as particle count in the region, any operator with a complete eigenbasis can be expanded like this, right? Where pi is an arbitrary projection operator that may not necessarily be a Ket-Bra, linear projection onto a line operator. It could be projected onto a plane, and so on. But and in this case, it's going to be a projection onto a high-dimensional space, right? The infinite dimensional, because there's an infinite number of points in any continuous region. But the interesting thing is that if you just extract one of these pi n, right, then that pi n corresponds to it's a binary observable with 2 eigenvalues, 0 and 1, corresponding to the question, are there exactly n particles in the region omega? I guess I'll decorate this with an omega too. Are there exactly n in omega? Are there exactly n particles in the region? So that's pretty cool. And like I said, you can do this, and you can do this same thing with regions even in first quantization. It's just that the number of particles that can be in there will be 0 and 1. But anyway, we often talk about averages in quantum mechanics, and I think discussion of probabilities is often sidelined. So I wanted to shine light on this. Sometimes you don't just want to know what's the expectation value for how many particles are in omega. Sometimes you want to know what the relative probabilities are of, like, if I make a little distribution, what's the probability that there are 0 particles, 1, 2, 3, and so on. There's got to be some number of particles in there. If I check how many particles are if I check how many particles are in omega, I want to know, what exactly the probabilities are of the different outcomes. And you can check that using these projection operators. Now, how do you actually construct those Projection operators. Well, you can't do it using field operators, I don't think. So, no, that's not true. Yeah, you can do it. Formally, it can be done. Formally, the probability the operator corresponding to the probability or probability density that any given observable lambda yields result lambda without a hat. I'll call it lambda not. It's a scalar. The operator corresponding to that probability is this, which can be made rigorous using a suitable expansion. Suitable expansion for the Dirac delta. So, use suitable expansion for the Dirac delta. Yeah. Right, so in our case, you could construct this operator using that technique. That's an n hat. Yeah, there you go. That would be your little spectral operator. So, yeah. Enjoy.